Welcome back to Valiant PE. Today's topic, toughness. Let's go. All right, like normal, we're going to go through a problem, we're going to solve it, and then we're going to go analyze what makes it a PE level problem. But before we get started, as we do with every problem, you want to prep yourself before starting. You've got 80 questions to go on a test. You got to give yourself some type of mental break between each question so you're reset and ready to go. So I like to take a deep breath, read the problem slowly, and then immediately write what I'm solving for in its units. So here we go. A manufacturer of steel chain wants to specify a new steel from which to manufacture their chain links. The new steel must have high toughness. Which of the four steels is most suitable? And so looking at the problem, I can see I've got some answer choices here, some imagery here, or some Young's modulus values and some imagery down here. Okay, so you can immediately tell there's no math. So what are we trying to do here? I think the concept we're trying to being asked about is toughness of steel in specific. So before we solve this problem, let's go learn a little bit about what toughness is. All right, so the first thing we can see is we have a curve or several curves given to us. Let's just take one as an example. And what on earth are we looking at here? This is the stress strain curve, one of the fundamentals of mechanics of materials. So you have strain on the bottom, and the y-axis is stress. And this is, the data on this chart is based on a tensile test, where you take a steel specimen, you pull it apart, and you watch how much it stretches until it breaks. There's a lot of videos out there on tensile testing. That's not the point of what we're doing here. But what can we get from this chart? Well, the first thing we see is we know the slope of that line is Young's modulus, which is basically the stiffness of the steel up to a certain point. When we get to here, we are no longer operating in a straight line. Anything in this area, we call that our elastic region. Elastic region. Okay. So now we're comfortable with stress strain curve. Let's move on to what exactly is this curve telling us. What we're going to deal with here, the main component, one of the two main components of toughness is strength. So we're going to go over what is strength and some of the things we find on this chart. So we've got strength is measured in pounds per square inch or megapascals, depending if you're in metric or standard. What is strength, and why do we need to know it to understand toughness? It's the ability of a material to withstand applied force. That's all it is. Same values as stress, measured in PSI. The next thing we need to know is when we are in the elastic region, this point here, when we get to this point, this is called our yield strength. And our yield strength means we can stretch the steel up to this point, it's going to snap back to its original location or original shape. Once we get past this point, though, now we're not in the elastic region anymore. So our yield strength, its definition, is the ability of a material to elastically deform before plastic deformation. Plastic deformation means permanent deformation. We've stretched the steel and it's not going to snap back to its original shape. And that happens at this point here. Something else we can determine from this graph is as we go up the graph, we get to a maximum point right here. That maximum value, sigma UTS, is called our ultimate tensile strength. And that is the maximum stress a material can absorb before failure begins. And this makes sense if we're basing this graph off the tensile test, because we're pulling a piece of steel apart. At some point it's going to start necking, and we're going to start down this portion of the curve until failure happens. So at this point here, we get fracture, which is the stress level at which a material breaks. Fracture. Okay, so that's pretty much all we can get from this graph as far as strength goes. The other component of toughness that we need to know is ductility. And what is ductility then? Its definition is the ability of a material to significantly deform and elongate before fracture. So when we're talking about strength, the higher the strength, the more load we can carry. With ductility, though, we're talking about how much can the steel stretch when it's under load. And it is measured in percent elongation and percent reduction in area. And these values are usually given in like some manufacturers' mill specifications or something if you order a piece of steel. Also, reduction in area, I believe, is given in the reference manual. So let's talk a little bit about what then does ductility mean. So in a tensile test, I've got this piece of steel here, and I put it in a machine and I basically pull it apart, put some axial force on it. If my material is brittle, I will see a non-smooth fracture surface. I will also see very little deformation in the region here. This will be a brittle material. If I have a ductile material, I'm going to see a lot of elongation. There's going to be a big stretch going on. I'm also going to see this here, necking. Necking is a dead indicator of I've got good ductility. And look at the fracture surface. It is much smoother, indicating kind of like a, as you pull it apart, it's stretching. And the big thing you're going to notice is look at the height difference. Look at my delta H between these two specimens. The ductile material is going to stretch more. So I think that's pretty obvious. That makes good sense. But how then does strength and ductility work together to give us toughness? Well, here it is. Toughness is basically, in layman's terms, the combination of strength and ductility. Just a combination. But since sometimes they can be kind of hard to quantify ductility, let's think in a different way of thinking about this. Let's think about how, in terms of energy, how much energy can a steel absorb? Rather than thinking about strength and ductility, let's think about energy. So that means if we can restate our definition of toughness, which we haven't given yet, never mind, let's do our definition of toughness. It's a measure of how much energy the steel can absorb through plastic deformation before fracture. And this is usually measured by the Sharpie or Charpie impact test or the IZOD test. Loads of videos out there about impact testing. So basically what we have here, combination of strength and ductility. That's what gives us toughness. Now that makes sense that a chain manufacturer would want a high yield strength, strong, and also a ductile steel. We want very high yield strength on our stress strain curves. We have a high elastic limit, can carry a high load, but we also want to be able to stretch so that the material doesn't just explode when it, as would be the case with brittle fracture. So if we could quantify this in terms of energy, how much energy can a steel absorb? So if we write toughness in regards to energy is given in these units, work per unit volume. So force times a distance, delta L, over a volume, inches cubed. And we can rewrite that as force over square inch times delta L over, I'm going to make a substitution here, LO. And that is the same thing as stress times strain. So looking back at our diagram here, how can we determine toughness from the stress strain diagram? And the answer is we want to maximize the area under the stress strain curve. So we draw a line straight down from our fracture point, and this entire area is an indicator, a measure of toughness, or how much energy the steel can absorb. All right, So let's go back and look at our answer choices and see what we've learned, how it applies. Okay, right off the bat, we can see that A has a very high yield strength, very high, but its ductility is not great. There's not a lot of stretch going on here. Conversely, the same thing is true for steel D. Very high ductility, way out here, but a pretty low yield strength. That's a terrible sigma. Let's do that again. Pretty low yield strength. That was not much better. So that leaves B and C. Okay, from inspection then, we can tell that B has a much greater area under the stress strain curve than does C. And so our answer is going to be B. And there you have it. Now notice that we didn't use our Young's modulus values. We'll get into that in just a second. But let's recap now toughness before we go into what makes this problem a PE level problem. Okay, so toughness is a combination of strength, which means we really want a high yield strength in this case, and a combination of ductility. We want it to deform before fracture. We don't want it to just break without any warning. We want to see some plastic deformation to give us some level of preparation. And this is all kind of quantified under energy absorption. How much energy can the steel absorb before fracture? Now, we didn't get into this, and we're not really going to in this video, but if you're going to apply toughness, it's really great in low temperature environments as a guard against brittleness and in impact loading scenarios. And there we have it. That's what we need to know about toughness. So lastly, let's get into what makes this problem a PE level problem. The first thing is that we can tell is this is a qualitative problem. Qualitative, which means there's no math. I didn't see any, we're not asked to solve for anything. I think the way to handle qualitative problems, and they are by far the hardest, is just have a basic understanding of the concept. I think if you can state in one or two sentences in your own words what toughness is, that's good enough. But the only way to get that understanding is to read the source material, and we cannot hammer this enough. Read, read, read. The reason people don't like this exam is because it takes so long to study for it. You have to read all the material that is listed in the exam specs, and the exam specs are super broad. They can ask you any question about any one of those topics, and you're going to have to know at least something about it. That's what makes qualitative problems so hard, and the only way to get there is read. Read, read, read. The next thing is, taken alone, this problem isn't really that hard, not by itself. But let's think about what components, what items did we need to know in order for us to be able to solve this problem? We needed to know about stress, strain, and Young's modulus. We needed to know about the stress-strain diagram. We needed to understand strength and ductility. These are terrible. There we go. And we need to know even a little bit about impact testing. So all of these items here, how would you have known about them if you hadn't taken the time to sit down and study? So building blocks put together really is how you solve a problem like this. Know the basics really well, and then you can solve a problem like this fast enough. Really, we didn't have to do any solving or problem solving here. We could answer this question really fast. But if you didn't understand things like stress and strain, Young's modulus, you didn't understand the diagram, there's no way you're going to be able to just do this problem quickly. So read, 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 study, study, study. And then the last thing, and this happens pretty frequently, we always get given extra information, and you need to be able to sort through what's important, what's relevant, what's not. Looking back at our problem here, we didn't need to know anything about Young's modulus. All we need to know was area under the curve. So that's it, folks. That's all there is to it. Remember, you don't have to be a genius to pass this exam. See you next time.